Let's continue. The natural progression from what we discussed in the previous lecture is to look at composite solid propellant combustion, which I used as an example to explain the importance of length scales of fuel and oxidizer supply and its connection to lateral diffusion and pressure. So, we will focus on solid propellant combustion starting from this lecture onwards. This is intended as a simple application of the ideas introduced so far. But before we go to the full description of the flame structure over a composite solid propellant, let us do a quick overview of the basics. So, this is how a solid rocket motor looks. A metal casing into which a propellant is filled, and the propellant cross section can have variety of shapes. Remember that the burning happens along the local normal, and therefore several different shapes are conceived to have a certain burning area variation with time. Okay, if you have a circular cross section, as the propellant burns, the area will increase with time, and if you have a block which burns, a cylindrical block which burns from one end, the area remains constant with time. It is also possible to construct grains where the burning happens from, in a cylindrical grain, the burning happens from inside to outside, but you start with special surface shapes, for example a star grain or a cylindrical grain attached to a phenol grain, as it is called. These can have complex burning surface evolution with time. For example, a star grain can be designed so that the burning area remains constant with time. Okay. So, the cross section can have variety of shapes, and depending on the size of the rocket motor, you have igniters of special kinds. It is usually a pyrogen igniter connected to an electrical connection to the squib. Okay. This is the converging part of the nozzle, the throat, and the diverging part. There is an insulation between the casing and the solid propellant. In case of long propellant grains, there can also be, the long propellant grains are made by putting together segments of grains, and there will be there can be insulations between or inhibitors between different sections of the grains also. Okay. The simplest the first question that we can ask about the behavior of a solid rocket motor is how the pressure inside, once ignited, how the pressure inside the rocket changes with time. Okay. This can be calculated from a simple mass balance. Okay. So, once the propellant is ignited, the solid propellant gets converted into hot gases, and that is the hot gas generation rate, which is controlled by the combustion rate of the propellant. Okay. And this will increase the quantity of gas inside the chamber, and therefore the pressure inside the chamber, and because of this the flow will start going out through the nozzle of the rocket. So, we have a burning solid propellant issuing hot gases into the chamber, into the port as it is called, and this will cause the hot gases to flow through the nozzle. Okay. And the nozzle, because of its dimensions, can accept only a certain dimension, and the thermodynamic state of the gases that are coming out can accept only a certain maximum flow condition under which the nozzle becomes choked. So, for a given upstream pressure and the thermodynamic state of the hot gases that are coming out, which by the way can be calculated from equilibrium calculation that we discussed yesterday, can actually admit only a certain maximum flow, under which conditions the nozzle becomes choked, and generation of more gases inside will simply increase the pressure inside the rocket, and the nozzle will continue to remain choked. Of course, the mass flow rate through the nozzle will increase because the pressure inside is changing, but the Mach number at the throat will remain 1. Okay. So, the pressure inside the port is controlled by the rate of generation of hot gases because of the combustion of the solid propellant, and the rate of outflow of hot gases through the nozzle. Okay. This controls the pressure inside this balance controls the pressure inside the rocket, and this we can simply calculate by a mass balance equation, which is the rate of change of mass in the port, okay, which is also equal to the mass inside the port is the density in the combustion chamber, or the density in the port multiplied by the volume of the port. So, the rate of change of mass inside the port is equal to the mass that comes into the port because of propellant combustion and the mass that goes out because of outflow through the nozzle. What I have done here in between is just I have expanded this equation. D by dt of rho c v is written as v d rho c by dt plus rho c dv by dt using chain rule, okay, and v d rho c by dt remains as it is, but the density inside the chamber multiplied by the rate of change of volume inside the chamber. See, the volume, you start with a certain volume inside the port, and as the propellant burns, that volume will increase, right. So, that increase in volume is nothing but the volume created by the conversion of the solid propellant into gases. This is nothing but the rate of burning of the propellant multiplied by the burning area of the propellant, okay, that is the increase in volume. Imagine a cylinder of radius r1 at time instant t1. Let us say at time instant t2 the radius increases from r1 to r2 because of the regression of the propellant normal to the surface or along the in the radial direction. The increase in volume is simply the area, which is the circumferential area multiplied by r2 minus r1. So, the rate of increase, perhaps this is something that I can just write it down just to make sure. So, you have the starting, let us say the starting diameter is this. So, you have start with the radius r1, okay, let us say this is the solid propellant, it is a cylindrical grain, okay, this is the radius at time t1. Let us say at time t2 the solid propellant burns and the radius increases to r2 at time t2, okay. So, now the port volume to begin with was this, the port volume to begin with was corresponding to a radius of r1. Now, the port volume at time t2 corresponds to a radius of r2. So, the change in volume is the volume at time t2, which is 2 pi, let us say the length is L, 2 pi L r, I am sorry, this is the volume, not the surface area, this is pi r1 squared, okay, times L is the volume of the cylinder, okay, at time t2 is r2 squared L minus pi r1 squared L, okay. So, this is the delta V, okay. From the delta V you can calculate a delta V by delta T as delta T goes to 0, you will get dV by dt, okay, okay. That you can show is nothing but the density of the propellant times the regression rate of the propellant multiplied by the area, burning area, okay. So, this is equal to, so the rate of change of mass inside the port is equal to the mass generation rate minus the mass outflow rate from mass conservation. So, now we have different terms, we have the density can be written as pressure divided by RTC, the pressure in the chamber divided by the RTC, the TC is the equilibrium temperature which does not change. So, it is constant, it does not change with time, it is only a function of the composition of the propellant. So, V by RTC dPc dt is equal to, I am just rearranging the equation, these terms go to the right. I must explain the rate of generation of gases will be equal to the rate of burning of the propellant multiplied by the density of the propellant multiplied by the area, which we just saw. The increase in volume, that volume would have become gases at a lower density, and that is this term rho p r dot AB. This is the rate of conversion of the solid propellant into gaseous propellant. The mass that is flowing out is the flow rate, is the mass flow rate through a choked nozzle, okay, where the gases are starting from a stagnation condition at a pressure equal to the chamber pressure. Okay. So, this mass flow through a choked nozzle, you have something like this, you have a pressure Pc here and the chamber temperature is Tc. The conditions at the throat are such that the Mach number at the throat is 1, that is a choked condition. Okay. The question that we are interested in is, what is the flow rate that goes through a nozzle that is choked with an upstream pressure of Pc, temperature Tc and a molecular weight of the gases flowing through, which is m. Okay, let me call it mw so that we do not confuse it with the Mach number. Okay. So, the mass flow rate through the nozzle m dot out is the density at the throat multiplied by the area of the throat multiplied by the velocity at the throat. Okay. The throat is choked, therefore, the Mach number at the throat is 1, therefore, velocity at the throat is equal to the sound speed corresponding to the local condition. So, this is density at the throat, area of the throat, square root of gamma r temperature at the throat. Okay. So, this is the mass flow rate through the nozzle. Now, what we do is that all the throat parameters, which is the density at the throat and the temperature at the throat, are related to the stagnation conditions upstream through the isentropic relations. Okay. The isentropic relation is that the total enthalpy at every point is the same. This is one part following from energy conservation, which also from here you can show that the total temperature is the temperature at the throat multiplied by gamma plus 1 by 2. Okay. And this is the adiabatic part, the isentropic part is PV raised to gamma equals constant, which also implies P over 1 minus gamma temperature raised to gamma is constant using the ideal gas equation. I am using V for both velocity, I should use mu for specific volume. Okay. One important thing to remember is that this R is not the universal gas constant, this is the specific gas constant. So, this R is a universal gas constant divided by the molecular weight, which is equal to 8.314 joules per mole Kelvin divided by the molecular weight. Okay. You can now plug all of these relations into this equation. You can show that m dot out is equal to Pc pressure in the chamber multiplied by the area of at the throat divided by a quantity called C star, called the characteristic velocity, where C star you can show if you do the algebraic manipulation, which I am skipping, you can show that this is R, the universal gas constant, multiplied by the temperature in the chamber square root divided by the molecular weight of the gases entering the nozzle divided by a function that is a function of gamma. Okay. Because of all these gammas appearing in the isentropic relationship, you will have a complicated looking function of gamma, but you can show that C star is equal to square root of Ru Tc by molecular weight. I am explicitly writing the specific gas constant as the universal gas constant divided by the molecular weight multiplied by a function of gamma. Function of gamma, it does not change a whole lot, gamma changes from 1.1 to 1.67 for monatomic gases. So, this does not change a whole lot. So, C star is a strong function of two things. One is the equilibrium temperature of the propellant combination. So, this is one use for the equilibrium composition or equilibrium calculation where you can get Tc. Okay. And the situation is such that that enough time is usually available in the combustion chamber for the reactions to go to equilibrium and reach the equilibrium temperature. The other most important factor is the molecular weight. Okay. So one of the reasons why, well, the reason why in the hydrogen oxygen system that the C star peaks at hydrogen rich conditions is because the molecular weight of hydrogen is 2 grams per mole, and therefore the value of C star, even though the temperatures are lower than what it is under stoichiometric conditions, the value of C star is much higher because there is a lot of hydrogen available. Okay. So the C star peaks under rich conditions even though the maximum temperature is close to stoichiometric. Okay. So C star is a fundamental thermodynamic property of the propellant composition. Okay. And it is related to the outflow through the nozzle by this relationship, okay, through this relationship. C star is a fundamental property of the propellant. The propellant combination, okay. Please go through the algebra. I have not done the entire algebra. Make sure that you get this equation by starting from here. Okay. So therefore the mass coming in is dependent on the rate of burning of the propellant. As expected, it is rho p r dot into burning surface area. This is because the propellant burns normal along the direction of the local normal, and the m dot out we just saw is Pc At by C star, where C star is a fundamental property of the propellant combination, which is equal to square root RTC. Here R is indeed the universal gas constant, the subscript U is missing, but this is the universal gas constant, which is 8.314 joules per mole Kelvin, because the molecular weight explicitly appears in the denominator. Okay. So C star will increase with increase in Tc, or the equilibrium temperature, but always keep in mind that molecular weight changes must be carefully accounted for, especially when you are dealing with species like hydrogen which have very low molecular weight compared to the oxidizer. Now this equation is now rearranged. We have V by RTC dPc dt is equal to rho p minus rho c r dot AB minus the outflow, which is Pc At by C star. Propellant densities, especially when you are looking at solid propellants, the propellant densities are much higher than the gas densities. Therefore the second term, which is the density of the gases, is much smaller than this and can be neglected. So the right hand side we are left with just two terms, which is rho p r dot AB, which is the rate of conversion of solid propellant into gaseous hot gases, minus Pc At by C star. Okay. You can scale this equation. The way it is done is we pull out Pc At by C star from the right hand side, so that the terms within the brackets are non-dimensional, and when you rearrange the equation you will get an equation of this kind, where you have L star, which is nothing but V divided by C star divided by it is V divided by C star, and you have 1 by Pc dPc dt. Okay, there is a time factor that you need to watch out for. Okay, I am sorry, let me correct myself. L star is simply V divided by At. Okay, that is L star. You have a gamma square and C star appearing from the simplification of the terms on the right, 1 by Pc dPc dt, and the right hand side is non-dimensional. Okay. The reason why I have highlighted this in blue color is L star over C star has dimensions of time. Okay. In fact, the typical time that is available for the gases to fill the port is about this time, and if you make an estimate of this quantity for a typical rocket, you will find that it is a few tens of milliseconds. Okay. And this is typically the time that is available for filling of the port, and therefore this is also the time that is approximately available for the gases to go to equilibrium, which is generally much higher than the chemical reaction rate times. Therefore assuming that the gases are at equilibrium is a very good approximation. Okay. So with this equation, the right hand side is non-dimensional. We will see how this equation behaves for different conditions. Okay. This will be the left hand side, this is the right hand side. Okay. We will take a typical example, a solid rocket motor with a port diameter of about 100 millimeters a throat diameter of 50 millimeters. The burn rate, remember, goes as A P raised to N. So, the way the burn rate expression is written here means the following. It is written as 10 millimeters per second multiplied by, it is written as 10 millimeters per second multiplied by P by 70 raised to 0.4. This means that the propellant has a burn rate of 10 mm per second at 70 atmospheres, because if you substitute P equals 70, the burn rate will become 10 millimeters per second, and at other pressures it changes as 10 multiplied by P by 70 raised to 0.4. The N value is 0.4, the A value is 10 mm per second at 70 atmospheres. Okay. The C star of a typical composite solid propellant will be in the range of 1700 meters per second. The propellant density will also be about 1700 kilograms per meter cube. Tau C is this quantity, L star divided by gamma squared C star, which is 11.5 milliseconds, which is plenty of time available for the reactants to go to equilibrium. Okay. And therefore, the C star value, which is calculated from the equilibrium result, is accurate. Okay. So, what is shown in this table here is, remember that the RHS is rho P R dot AB divided by PCAT by C star minus 1, and the left hand side is this quantity. What I have done is, for various values of chamber pressure, I have calculated the RHS values. Okay. So, at what this means is that at 20 atmospheres, the right hand side is a positive number. So, the left hand side is dPc dt and the right hand side is a positive number. That means if you start from 20 atmospheres, dPc dt is positive and the pressure will increase. Okay. So, the pressure will increase till a point where the right hand side becomes 0, because dPc dt equals 0 means the pressure is constant, it cannot change once it reaches that point. So, if you start from 20 atmospheres, the right hand side is positive, the pressure will increase, the magnitude of the right hand side term will slowly decrease as the pressure increases, and there will come a particular pressure at which the right hand side is 0. That is the equilibrium pressure at which the rocket will settle down. Okay. That in this case is 112 atmospheres. Instead, if you started from a value that is higher than 112 atmospheres, let us say you start from 150 atmospheres, obviously as expected the right hand side is negative. So, the pressure will decrease till this point when pressure becomes 112 and then stop there. Okay. So, this 112 atmospheres is called the equilibrium pressure. Okay. So, if you build a rocket and you want to calculate the equilibrium pressure is the pressure at which the left hand side is 0. That means these terms, the mass generation rate and the mass outflow rate are exactly matched. Okay. In reality, it has to be done in a quasi-static fashion, because remember that at different instances of time the burning area will also change, and that is how it is done in using ballistic codes when developing solid rockets. Okay. But the reason why I brought this up is for a different reason and a fundamental reason. This behavior, this equilibrium state where dPc dt is 0 can be stable or it can be unstable. What I mean by that is, look at the graphs that I have shown on the right bottom. It is a plot of chamber pressure, okay, versus m dot in and m dot out. Remember that m dot out goes as PCAT by C star, therefore for a fixed throat and a fixed propellant composition, the exit mass flow rate will linearly increase with pressure, okay, and that is what I have shown with the line in the center. It is a straight line which is m dot out, okay, and the other two curves are the mass generation rate, which is because of the combustion of the propellant. Okay. As you can see, the combustion of the propellant or the mass generation rate because of the combustion of the propellant goes as rho P R dot AB, and R dot itself goes as A P raised to N. Okay. So, when N is less than 1, that means the pressure, the burn rate pressure index of the propellant is less than 1, the mass generation rate will change like this. For the n less than 1 case, you can see two curves, one marked n less than 1, one marked n greater than 1. The n less than 1 curve goes above the straight line till some pressure and then crosses the straight line at a certain pressure, the point where it crosses over is the equilibrium point, that is where the right hand side is 0, okay, and that is equilibrium pressure. So, if you drop a vertical from that point, you will get 112 atmospheres for the case which I described in the previous slide. Remember that the index of this propellant was 0.4, therefore n was less than 1, and therefore this curve and the straight line are representative of what is happening in this rocket. And now if you are at the equilibrium point for this case, let us say there is some perturbation that brings down the pressure, okay. I think I better explain this in some detail, okay. What I am talking about is, this is the chamber pressure, this is Pc AT by C star. When n is less than 1, the mass burn rate of the propellant behaves like this is n less than 1, okay. This is the equilibrium point, this is the equilibrium point, okay. So, if you start from a pressure that is less than the equilibrium pressure, the mass generation rate is greater than the mass outflow, therefore the right hand side is positive, the pressure will increase and come to the equilibrium value, okay. You start from here, you will go to the equilibrium point, okay. Instead, if you start from a higher pressure, the mass generation rate is smaller than the mass outflow rate, therefore the right hand side is negative, this will automatically push you to the equilibrium point, okay. So, any tiny perturbation that causes the chamber pressure to either go down or go up is not very serious, because you will get automatically, the rocket will automatically go back to the point of equilibrium, because that is how the relationship between the inflow and the outflow are, okay. This is the case when n is less than 1, but consider the case where n is greater than 1, okay. Let us say this n is greater than 1, okay. Here also the equilibrium point is here, but if you start from a point that is at a pressure lower than the equilibrium pressure, the outflow rate is greater than the mass generation rate, that means the right hand side is negative, okay. So, it will actually, if you start here, it will push you towards the origin, okay. And if you start here on the at a pressure that is above the equilibrium pressure, the mass generation rate is more than the mass outflow rate, that means the right hand side is positive and the pressure will continue to increase, okay. So, by some delicate balance, if you started at the equilibrium point, any tiny disturbance will either push the rocket towards 0 pressure, or the pressure will blow up and the rocket will explode, okay. So, n less than 1, the equilibrium point is stable, and n greater than 1, the equilibrium point is unstable. What we mean by that? You can imagine something like this, the stable equilibrium is like this, the rocket is sitting at a state that is here, you push it a little to the left, a little to the right, it will come back to the equilibrium point. But n greater than 1 is as if the rocket operating point is sitting on top of a hill, you push it a little to the left, push it a little to the right, it will run away from the equilibrium point, okay. But as it turns out, for all composite solid propellants, the index is usually less than 1. And therefore, they are statically stable. So, they are statically stable. So, static stability is always ensured with composite solid propellants, okay. This is Pc AT by C star, and this is rho P A Pc raised to n AB. So, n less than 1, the curve goes like this, n greater than 1, the curve goes like this. Is that clear? So, that is what I was trying to explain. So, for n less than 1, you have at pressures lower than the equilibrium pressures, right hand side is positive, you are pushed to the equilibrium point. For pressures greater than the equilibrium pressure, the right hand side is negative, again you are pushed to the equilibrium point. If n is greater than 1, this order will be flipped. So, you will be pushed away from the equilibrium point, therefore, the equilibrium point for n greater than 1 is unstable. So, the condition for static stability is that the index must be less than 1, and at equilibrium where the left hand side is 0, dPc dt is 0, the mass generation rate is balanced by the mass production rate. Should say it the other way around, the left hand side is the mass generation rate, the right hand side is the mass outflow, and with r dot equals Ap raised to n, this will give you an expression of this kind. The equilibrium pressure is dependent on the ratio of the burning surface area to the throat area multiplied by C star divided by A rho P raised to 1 by 1 minus n. In practice, it is generally preferred to have as low a value for n as possible. There are several reasons for that, but the most important reason, as you can see from the table, is for a n value of 0.2, okay, if there is some process that causes a change or a abrupt change in the area of the burning surface, okay, there could be cracks in the propellant which can create a perturbation in the burning surface area. This will lead to a change in pressure which is 1.25 times, the differential change is 1.25, and the corresponding change in percentage change in thrust is a factor of 1.25, okay. On the other hand, if you have an n value of 0.7, this can lead to a large change. It can lead to a change in pressure that is about 3 times of what you get at n equals 0.2, and the thrust change is corresponding 3%. The other factor is, if there is a small crack and the index is large, it will quickly become, it will lead to a quick increase in the burning surface area, because the crack can propagate because of further burning of the propellant, okay. So, this is the most important limitation in seeking compositions with lower index. The other things are can be controlled in a much better way than the burning surface area of the propellant. Anyway, I will not go into the details of this as this is for a rocket propulsion course. We are not looking at rocket propulsion per se, okay. The next topic is something to do with r dot equals Apc raised to n, called erosive burning, and I will hand it over to Professor Mukunda for this.